So this lesson on strong and weak acids and bases is a follow-up to my previous lesson where I differentiate between the Arrhenius and Bronsted-Lowry theories of acids and bases. And so we're going to talk today about, well, what makes an acid strong and what makes an acid weak. So I want you to envision that, before scientists had necessarily had knowledge of what was making one acid more potent than another, they might have tested two acids with the same concentration. So let's say here I have an acid with a concentration of 1.0 moles per liter, and another one with 1.0 moles per liter. And scientists may have expected that each of those solutions would have basically equal conductivity. And to their surprise, they would have seen that that was not necessarily the case. And so those acids that were able to conduct very, very well, we called strong. And those acids that maybe were still able to conduct but not quite as well, we might have labeled them as weak. And so, well, what is at the root cause of that? So I want you to start thinking about, well, what causes a solution to be a very strong conductor of electricity versus maybe a less good conductor of electricity? So let's talk about that. So as we saw in the previous slide, the strength of the acid is not really related to its concentration. For instance, I could have a weak acid that had a concentration of 2.0 moles per liter, and I could have a strong acid with a concentration of 1.0 moles per liter, right? So, it's really not about the concentration. That has to do with the number of moles in a given volume of solution, whereas weak and strong has to do with the degree to which an acid or base is able to dissociate or ionize in water, liberating, if it's an acid, those hydronium ions, and if it's a base, those hydroxide ions, right? And so, so let's talk a little bit more about that. We're going to talk about how we might differentiate between them. So let's take a look. Before we do that, I want to differentiate for you the terms ionization and dissociation. So ionization is, when you take a particle that is neutral and you create ions. So let me give you an example of that. So a great example of that would be if I were to take ammonia and hydrolyze it using water. And if it's acting as a base, it might accept a proton, and we would get ammonium as a result, as well as hydroxide. And so our ammonium ion formed from a molecule. Okay, so the ammonia is a molecule, whereas ammonium is an ion, right? We formed ions where there were none before. Now I want to juxtapose this to dissociation, where we have the separation of charged particles, where those cations and anions already exist in that compound. So we would say that ionic compounds dissociate. So for instance, if I had sodium hydroxide, that is an ionic compound, and so we would say that it dissociates into sodium cations and hydroxide anions. Okay, and so here we have our ionic compound that is freeing up ions. Okay, so that's dissociation and that is ionization. I hope that's clear. It's a subtle difference, but it matters in terms of the language that we use. So let's take a look at strong acids and bases and define them a little bit more. So a strong acid is one where when in water, it will, you'll see 100% ionization. Okay, so if, for instance, I had 100 molecules of HCl here in water, then all 100 of them would donate a proton to water and form that hydronium ion. Okay, 100% dissociation or ionization. And so the same holds true for bases. So if I had, let's say, for instance, 100 molecules, or particles, I should say, of sodium hydroxide, then all 100 of them would dissociate into sodium ions and hydroxide ions, or near 100. Okay, and so that frees up some ions to do some damage, like these hydroxide ions, for instance. Okay, now conversely, weak acids and bases are not going to dissociate 100%. If we were to zoom in on a strong acid, we would see that all of the particles will have dissociated. I'm going to assume this is a proton and that this is the anion that would be with that proton. In a weak acid, we would see, although some of the protons would have dissociated and be present in solution, a good proportion of the original acid would remain undissociated. So let's look at that. So weak acids or bases are characterized by a less than 50% ionization. And in grade 12 chemistry, we will mathify this. We'll look at doing some calculations around this, where we will be able to identify the percent ionization of a particular weak acid or weak base. Okay, so a weak acid or base would be one where we might see 100 molecules of the original acid. This is acetic acid, by the way, and only a small proportion. In this case, I've said 10 out of 100, or 10%, might dissociate. So, we're freeing up fewer hydronium ions or hydrogen ions in solution, and so you're going to see it not having the same sort of effect. So in the same way, if we start off with a proportion of ammonia molecules, we would end up with, less than 50 dissociating in solution. So that's it. That's all there is to it. When we define a strong acid versus a weak acid and a strong base versus a weak base, we're looking at the percent ionization or dissociation, understanding that strong acids and bases will ionize or dissociate 100% or close to it, and we'll see far less dissociation in our weak acids and bases. So stay tuned for next year, because next year we will mathify this. Make sure to ask questions if you have any.